Hi, this is James Cook of the University of Maine at Augusta, and I'm shooting this video today to talk about visualization options for social networks within R. This is not an intermediate or advanced introduction, but a really basic introduction for those who are just getting started using R and a package called iGraph to create network graphs from other representations of social networks. Those might be an edge list, an adjacency list, but also an adjacency matrix, which is perhaps the most classic way of representing a social network in a non-pictorial fashion. So let's take a look at an adjacency matrix, which we might find in perhaps Microsoft Excel. This is an example with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 individuals, Al through Leo, each representing a letter of the alphabet. And each of them has a column, each of them has a row. And the spaces where there are ones indicate the presence of a tie between a combination of a row and a column. So Al and Betty have a 1, which means that they are perhaps friends. In fact, you can see everywhere that one person from a row is connected to someone with a column, it goes the other way. And that's a sign that this is a symmetric network and most likely a network without any kind of direction. So it might be people who go out to dinner together or go out to see movies together on a regular basis or attend church together. These are the kinds of shared activities that it's impossible to have direction for because you can't have one person go to church with the other and have it not go the other way around. So we have here an adjacency matrix. Adjacency is an idea, it's a word that means is next to, is connected to. This is a mathematical pattern of connection where 1 means yes, 0 means no. And not everyone is tied in this network, but some people are. Well, we've learned in a previous video how to write a program called a script in R, which is just a series of commands that go through and read that CSV file after starting iGraph, library iGraph, loading that in, and then after that, saying, hey, this is a matrix. And after that, saying, hey, this is not just a matrix, it's an adjacency matrix, which is a representation of a social network. We can then print that social network. And then in iGraph, we can use the plot command to create an image of a social network called a social network graph. So let's start by running this program and seeing what R throws at us. Okay, so I'm going to select this editor window and then hit edit and find the command for running all. Okay, and I notice it's working on it. It's asking me to select a file, which I'll do, heading up to R. And I'm going to find that file for that particular matrix that we were looking at before. And then under Windows, I'm going to look for a picture. And this picture is going to show a network. The network, I'm going to move right over here so we can look at that graph. That network is a series of dots called nodes, a series of lines called ties, and they're together in a pattern in a structure. Now we might stop there, but I'd like to today suggest that we don't, because the very arrangement of that by R represents a series of choices. The particular choice that they're engaging in here by default is something called a spring embedding and enforce related way of thinking about placing nodes next to each other. So you can think of those ties like springs, right? And those springs really, when they're stretched out, they want to pull back together. So the physics that are used to create this picture imagine that when there are ties, they pull back in. They pull the nodes back in toward one another like a spring that's been pulled too far. And at the same time, nodes tend to want to stay away from each other. So they repel like electrons or protons or two magnets with the north pole facing one another. So the nodes are repelling each other, but the springs are pulling them back in. And what that results in is a picture in which sets of nodes that are tied closely, clustered closely to one another, end up being held together and resisting that urge to fly off. Whereas nodes that are not connected to each other, like Leo at the top here and Al at the bottom here, tend to be repelled and to stay away from each other. And there's nothing to make them come close together, except a very long series of intermediate ties. Well, that's an image. That's an idea about what we ought to pay attention to in the network. And this image makes us see it. We have no choice but to see it, unless we start to change some of the ways that we visualize this network. And so a way we can do that is by modifying this plot. And the first way I want to modify this plot is by adding a layout option. Layout equals. So this is in the parentheses. It's an option to talk about what's going on in the plot. The first option in the plot is, well, what do you want to plot? And the answer is my second network, which is this network that we've uploaded, this adjacency matrix. It's being shown as a graph. The second option now that we can specify is, what kind of layout do you want? And one answer is going to always be that layout equals layout dot something. A particular kind of layout. One kind of layout we could do is random. What happens if we just have these nodes appearing at random? What would that look like? Well, let's now run our script again. And the nice thing about having this script is that we don't have to type it all out again. We just have to change one thing, run it. And of course, we have to select our material again, but that's okay. This is random. Okay. So every time I run this, if I run it again, it'll look different. And it'll ask me to load it again. And it looks different. So I'm actually now going to, we know what the data is. I'm going to comment that out so we don't have to do that each time. It's going to look different again and again and again. And one of the things you might notice is that compared to the other picture, every time we run this random set, we get a different idea of what might matter, what is salient, who's in the middle, who's in the center of this network. So right now, boy, it looks like Jack is in the middle, and Betty and Gus and Fran, and it looks like, Al and Edna are kind of on the outside looking in. But if we reload and do this random layout again, all of a sudden Edna now is in the middle. And Gus is kind of not too far out, but sort of on the outside. And there's a whole lot of overlap as well, a whole lot of mess. So if we take away that random layout and replace it again with this idea that we should organize it according to clusters of individuals who are connected to each other, we get a very different image. It's an organized image, and it's one that tells us, well, Edna and Fran seem to be in the middle, and Leo and Al seem to be on the outside. What about Clem and Dot? Dot looks a little closer, but actually structurally is no closer than Clem is. It's just that Clem was chosen to move to the outside. So there is still some assumptions that are going on in here, and we can still start to look at some kind of different ways of looking at things. So instead of simply plotting this standard spring embedded network, we could think about another kind of assumption that we could work with. And that would be a layout that I particularly like, called Rheingold-Tilford. And when we work with that Rheingold-Tilford visualization, we're going to focus on one central node and think about how all other nodes relate to that one. Let's pick one by typing layout Rheingold.Tilford. I'm then going to have to specify again that in my second network, we're going to look at a particular root from which a whole tree of the network grows. That's the image. And that root, let's just pick as Inez. We'll want to put that in quotes. And then it looks like I'll need to have, since I have 1, 2 beginning parentheses, I'll need to have 1, 2 ending parentheses. Let's see how that looks when we look at the network from the point of view of Inez. And we're going to see all other nodes organized according to how far away they are from Inez. So let's try running that and see what we get. So here's Inez at the top. And then there are 4 individuals in a row right underneath Inez: Fran, Howie, Jack, and Chrissy. And they are network distance of 1 away, 1 intervening tie. The next row is those that are 2 intervening ties away. The next row, 3, and then 1 after that, 4. So from this point of view, it looks like Inez is really at the center and is at the top almost, right? This almost looks like an organizational chart. She seems like the one that's in charge, whereas other individuals are a little lower on the totem pole. It leads us to focus our eyes on Inez. Of course, we could select another individual, like Edna, for instance, and we'll simply do that and run this again. And now, where's Inez? Oh, she's on the 3rd layer. She doesn't look like she matters too much. However, we can see very closely who's closest to Edna and who's farthest away from Edna, and how Edna actually separates the network into these 2 distinct groups, one of which is Betty, Al, Clem, and Dot, and the other one which is everybody else. That's really interesting to know. It's important to know. And if we have a reason to believe that Edna is really important from the get-go, this is a kind of visualization that can tell us how the network revolves around her. But if we don't think of Edna in any special way from the beginning, this might not be the kind of visualization we want to engage in, because it's prioritizing Edna, and perhaps not altogether fairly. Because if we take away that assumption and we just return to this Spring embedding standard, well, Edna is reasonably central, but she's not the one who's most in the middle in terms of closeness. She's actually a little off to the side. Perhaps Gus and Fran or Howie are a little bit more important in that network, depending on how you measure centrality. So there are some other options that are available for visualization as well, and we could think about those. One of the things we could do is that we could simply lay out individuals in a circle. To say layout equals layout dot circle. Well, what would that look like? It would certainly look pretty. It would look pretty cool. But what does that tell us? There are some ties that span the entire circle. There are some ties that are short. Does that length mean anything? Not really. This is a favorite kind of layout for people who are interested in doing social network analysis, because it looks really cool. It looks like it tells us who's close to whom, but you'll notice Fran and Inez are no farther apart from each other in network terms than Fran and Edna, but they certainly are in graphic terms. There's a big long line between them. The same in terms of Edna and Betty. They seem far away from each other. Edna and Dot, on the other hand, seem closer to each other, but Dot and Edna are at a network distance of 2 from each other. 2 intervening ties. So this Circle is not necessarily the most accurate. We could also think about a grid kind of format in which every dot is evenly placed, and so they're all equidistant from one another. And that looks like hierarchy. It looks like there are some on top and some are on the bottom, but top and bottom are really not organized in any meaningful way in terms of the structure of the network. In fact, if we look, it looks like R started with the beginning of the alphabet, A, Al, then B, Betty, then Clem, then Dot, then Edna, then Fran, then Gus, then Howie, then Inez, then Jack, then Chrissy, and Leo. It's organized alphabetically. So being on the top versus being on the bottom, being close versus being far, it's not well organized in this grid. So those options for layout may not be as meaningful as spring embedding or this notion of working with a tree and thinking about who's in the middle and who's not. So let's return to our spring embedded model. The idea that nodes are drawn toward each other when they're tied, and otherwise they're pushed away from each other if they're not. Here we are again. So this is R's standard in some other ways. We have some orange circles tied together by some gray lines, and they're all the same size, but they're not all the same. Even though we know nothing about the internal psychology of Al or Clem or Edna or Leo or Jack or Chrissy, we don't know what drives their hearts in this social network model. We do know some things about their position, and we can find out some things about their position. For instance, we can find out some things about their betweenness, okay, and their closeness. So their betweenness and their closeness are what? They're measures of centrality. They're measures of centrality. We can find out about their degree, and their degree is also a measure of centrality. So let's take a look at some of those, and we can find out some things about those very quickly by typing in just a few commands. So betweenness is a measure of centrality that asks, when these closest paths from one node to another, the shortest paths to get from one node to another occur, how often is any particular node happening to be in the middle? That is, if this side of the network wants to get over to that side of the network, who do they have to go through most of the time? So betweenness can be measured by simply typing in betweenness in a parenthesis and then typing in the name of the network, which is my second network here. That's just the name of the network. And then we'll need to know one more thing, which is whether this is a directed network or not. And in this case, it's not. So we'll say, oh, it's false that it is directed, which is a way to say that it's undirected. Now, we could also measure some other kinds of measures of centrality, of mattering in a network. One of those might be degree. Degree is simply the number of ties that is associated with a particular node. We can say offhand, just looking at Al here and Leo here, they each only have one tie to one other node, and that's a low degree, a degree of 1. We can look at Betty, on the other hand, and say, wow, she has 1, 2, 3, 4. That's a lot of connections. If we have a very large network, we would want to compute this and let the not by hand, but let the computer do it. And to do that, we'd type in degree and then the name of the network, which here is called my second network. And then we would have to specify, well, gosh, is this an undirected network? If so, we want to count all ties. So mode equals all. Let's count all ties in degree. Now, when we do that, I'm going to skip away from this picture of the network graph, and we're going to go over to the console, which shows us the text output. And I'm going to run this script, and it'll tell us, in terms of betweenness and in terms of degree, who's really got it going on and who doesn't. Now, for betweenness, we can see right here, Al, Clem, dot, and Leo have a betweenness of 0. Why would that be? Al, Clem, dot, and Leo. It's because Clem, dot, Al, and Leo are not in the middle of anything. They're all on the edges. Although Clem can be tied to dot, and you could talk about maybe Betty going to Clem to dot back to Betty. That's not the most efficient path. In the most efficient path, the shortest paths, otherwise known as geodesics, Clem and dot aren't in the middle of any of that. Neither is Al, neither is Leo, not in the middle of any path, which is why their betweenness centrality is 0. On the other hand, if we look at the highest centrality values, they're Edna and Betty, and then Inez and Fran. Why are Betty and Edna so central in this network? Because there's no way to get through from one side of the network to the other without going through them. In fact, they're kind of a bottleneck here, aren't they? They're kind of a bottleneck. You can't possibly get over here from over here, or vice versa, without going through Betty and Edna. They're the gatekeepers. That's what this betweenness centrality is all about. So Betty and Edna are also relatively high on degree. Betty has 4 ties, Edna has 3. Howie and Chrissy and Jack each also have 3, and Inez has 4. But look at betweenness versus degree. Howie and has a rarely high degree, but doesn't have a very high betweenness. And Jack, who has a fairly high degree, has a really low betweenness. Why is that? Because Jack is kind of out on the side. Here's Jack. Jack is tied to a lot of individuals, but kind of on one end of the network, and there are other ways to get through to those other people besides Jack. If Jack decides to not pass on word to Chrissy about something from Howie, well, Howie can get word to Chrissy through Inez. And there's a whole other path that bypasses Jack entirely from this side of the network here. So these are 2 different measures of mattering in a network, this structural position that changes how you interact with others, what your experience might be. And in terms of visualization, we might want to change the way that the network looks in order to reflect that. So in order to do that, we can go back to the plot. So here we've calculated in our script betweenness, and then we calculated degree, and we calculated it for every single node. So having done that, we can start to take a look at some different ways of representing these nodes in the plot. So we can do that by adding, again, another kind of option, a modification to the plot. And in this one, we could modify vertex size. Now, you can just modify vertex size for every vertex in the entire network. So the standard size, I believe, is 15. So if we said, oh, let's make all the vertices size 25, and then we ran that, well, they'd all be bigger. That's nice. That's a little bit more colorful in terms of the presence of color on that background of white, but it doesn't still tell us anything. So what if instead of simply setting that number to something higher than 25, we allowed it to vary? Let's look at the values for degree. Okay, so we're going back here to degree. Degree sits between 1 and 4. Okay, so those numbers are going to be 1, 2, 3, or 4. Well, the size of the vertices, the nodes, as we would call them in social network analysis, but are called vertices here because that's a graph theoretic term. The standard is 15, right? And some might be larger than 15, some might be smaller than 15. So how would we get from a number that varies from 1 to 4 to something that kind of circulates around 15, 20, somewhere around there? Well, we could multiply that by, well, what's some multiplying by 8? 1 times 8 is 8, 2 times 8 is 16, 3 times 8 is 24, 4 times 8 is 32. Okay, so we could take the vertex size and we could make that equal to the degree in my second network. And we could multiply that by 8, star 8. Star means multiplication. I'm going to press return so it's all on the same page here. So if we take that vertex size and we make it equal to whatever the degree is for a node, and we multiply that by 8, we'll get variation. Let's see what it looks like. And we'll hit edit and run all. Oh, wow. Okay, that's really interesting now all of a sudden. We can see visually that Al and Leo are small players. They only have that one, right? They have that one connection, whereas Betty, Inez, and then Edna, Howie, and Chrissy and Jack a little bit are the major players here. Okay, Betty and Inez we can see really are swallowing up a lot of that work. If we, on the other hand, replaced size with from degree and we made that equal to betweenness, well, what's the value of betweenness? It's anywhere between 0 and 30. So we might want to only say multiply that by, I don't know, 2, or maybe not at all, maybe even just 1.5 to make it a little big, and then run that. Okay, we're then going to need to open up the graphics window, and we'll see a different picture. Whereas Betty looked really big and really important there, Edna is now magnified here in importance. Inez, which was tied for Betty for the lead, is kind of a second string player. Howie certainly and Jack certainly are much diminished because they're not in the middle of everything. So this is a really neat way to kind of visualize importance. You could do two at once by looking at not just vertex size, but you could look at vertex color at the same time. Let's put that on a different line. So that vertex dot color might be equal to then degree and of my second network. And the nice thing that R does is that it creates different colors according to different numbers. You have to experiment with this to get an idea of the range of colors according to the range of numbers. For instance, if we leave just degree alone, which we know from the text results over here is between 1 and 4 for the nodes in the network. If we just leave degree alone and don't modify it by any multiplier to make it bigger, we would, going over to edit to run it all, we would see not too much variation in color. Although there's a little bit there. Okay, we could multiply that. What if we multiply that by 100? What does it look different? Or does R handle that? Oh, actually, it creates a different palette. So we have the idea that, I wonder if we get different colors altogether if we just go down to 99. We do. It looks like each individual color has a number. And so regardless of what different kinds of numbers we pick, what about 1,999? Would we still get color variation? We sure would. And it would be a little odd sometimes here. It doesn't seem to be working very well because the degree for Chrissy and Howie seems to be similar to that for Edna. But if we go back to, say, maybe 1 or 2, we'll get some differentiation there. Okay, and we can start to think about color. Does color work here? These adjacent colors showing different degrees? Maybe not so much, maybe not as well. But we could continue to play with these ideas to think about how size and color together can show us different dimensions simultaneously of what's going on in a network. And then when we add in something like layout in addition, so that we are making layout equal to layout Rheingold dot Tilford, and then making that equal to my second network. Picking an individual in there that we have learned through looking at this is really kind of important. Boy, Edna seems to be important, or maybe Betty is important. Let's pick Edna again, and we make that root equal to Edna. And put a comma in there to connect it to all the rest of the other options. And we run that. Now we've got an arrangement of nodes, we've got a size of nodes, we've got color of nodes to have an indication of some kind of hierarchical structure that's really quite interesting. When you have a network that's a lot bigger than this network, where you may not know each person individually, as we might with these 12 individuals here that we've studied, if you have 1,000 nodes, this is a great way to be able to immediately look at a pattern in 1,000 nodes and be able to pick out just a few individuals who seem to be central in the network, who seem to be big players by one standard or another: betweenness centrality, degree centrality, closeness centrality, and to go ahead from there and figure out who they are, what makes them important, what makes them different from those around them. I hope that this illustration of the idea of working with a network and doing some examination along multiple dimensions of structure through your eyes, through visualization, has been helpful.